So this leads us to the idea of a buffer. And a buffer is a real important system in science. It is used a lot in chemistry, but arguably, I would argue that biology and medicine uses this even more. A buffer is just a solution that resists changes to the pH of a solution, all right? And if you want to have a solution which is not affected by pH, at least not as much, you want to use a buffer. And buffers are really just a special case of this common ion effect we talked about earlier. In a buffer, you have to have a weak acid and its conjugate base. So, for example, you could have acetic acid there and acetate. You could have dihydrogen phosphate and hydrogen phosphate. Remember, the acid always has more hydrogen than the base, if you're uncertain, by the way. You can also have, though, a weak base and its conjugate acid. So the ammonium example we looked at earlier would be a great example of this. As we go into buffers, I want to make a small advertisement for a handout which I think will be really helpful to you. And that handout is called the Buffers and Henderson Hasselbot Guide. I'll talk about Henderson Hasselbot here in a little bit, but this guide talks a lot more detail about how buffers work and how you can quickly calculate the pH of a buffer or the pH upon adding acids and bases. So keep that handout in the back of your mind. This question says, which combination would be an ideal buffer solution? Okay, so in a buffer, you must have a weak acid and its conjugate base or a weak base and its conjugate acid. Every time you see a strong acid or a strong base, you should disqualify that solution immediately. And if you look at these, there's a lot of them. HNO3, strong acid, pull it. HCl and KOH, strong acid, strong base, pull that one out. So it's going to be either C, D, or possibly E. I'll let you know it's not E, by the way. But anyway, we have to figure out a buffer system where you have a weak acid and its conjugate base. If you look at answer D, ammonia is certainly a weak base, absolutely. But that CH3, NH3, Cl thing, that certainly is not a base, or that's not a conjugate base specifically of NH3. Remember, conjugates are related by H plus or minus. So NH3 plus H plus would be NH4 plus, and that CH3, NH3, Cl thing, that certainly is not the buffer. So that's not going to be the conjugate base for ammonia. That's going to be something else. C at first doesn't maybe look like it's a conjugate system, but this first compound, CH3CO2H, that's acetic acid. That's the HOAC thing I keep writing in lectures. And the conjugate base of acetic acid would be everything I just underlined without the H plus. So that would be CH3CO2 minus 1. And this thing over here on the right, the other species, it has a sodium ion. Sodium is positive 1. And a lot of times the things which are negative ions, they'll be complexed with a sodium or potassium ion. So if you would take the Na plus off, you would end up with CH3CO2 minus 1. That's the acetate ion, and that is the conjugate of acetic acid. So the only one up there that's valid for a buffer would be answer C. And I put that up there because you can see that with the sodium, it didn't really look like it was a conjugate, but it is. To add an acetate source to solution, you need to complex it with an ion. So you can measure out sodium acetate, and when you measure it out and put it in water, the sodium goes its own way. It's a spectator ion. You then have the acetate to complement acetic acid. Don't worry about the concentrations, the moles per liter right now. In this problem, we just want to see which one is possibly a buffer, and you must have a weak acid and its conjugate base or a weak base and its conjugate acid. Buffers have a lot of uses, not only on an industrial scale, but also on a biological or medical version. And this is a really important example because we're all using it right now as we watch, or I'm making this video. Blood is actually buffered against strong pH changes. And that's really good. If you want to have a functioning organism, i.e. you want to live, you want to have a blood system which isn't just going to spike and go crazy if you accidentally add a little heavy acid or heavy base for that matter. And so this carbonic acid buffer system, and carbonic acid is H2CO3, is really something that's really helpful. Carbon dioxide and water are in equilibrium with a carbonic acid solution. And carbonic acid itself then, which has an acid, it's a diprotic acid because it has two acidic H pluses. Anyway, the first one especially comes off pretty readily. And that hydrogen carbonate then does lots of things. And there's a bicarbonate reserve you'll talk about in biology, which is really cool. We're going to see that having a buffered system in our bodies is going to be really important. If you exhale CO2, you're getting rid of the acid. If CO2 starts going away, if it exhales out, then the equilibrium shifts to the left. Carbonic acid begins to turn into more CO2 and water. If you have less acid, the pH is going to go up. All right, this is another example, common ion. So you exhale a lot of CO2, you're going to have the carbonic acid shift to the CO2 and water. So less acid means it's going to become more basic. Your pH will go up and down a little bit in your blood, a little bit, and that's natural. Again, you'll learn a lot more about this in biology. I'm way over my lines. I love buffers, and I can talk about buffers forever, but the practical things I am not as good at. The Lame Instructor Confessions 101.
The pH of a beaker of ordinary tap water is 6.29, slightly acidic because small amounts of carbon dioxide are dissolved in it. When we add a 0.1 molar solution of hydrochloric acid to the beaker, the water shows a large change in pH. Water is not a buffered solution.
In this example, we're adding hydrochloric acid to pure water. And notice the pH change. All right, in the little pH probe there, it went from a number which was around 7 down to 1.8. All right, and that wasn't actually a lot of hydrochloric acid that was added, but you can see the effect on the pH. HCl, a strong acid, will dominate the landscape. Sodium hydroxide, strong bases, would do the same. But anyway, HCl, a strong acid added to water, creates a huge pH change. Now we're going to look at the same example of hydrochloric acid, but when it's added to a buffer.
In the beaker is a mixture of dissolved dihydrogen phosphate ion and its conjugate base, hydrogen phosphate ion. The solution has a pH of 6.92. We add 10 milliliters of a 0.1 molar solution of hydrochloric acid, which causes only a small decrease in pH to 6.72. The solution is said to be buffered by the conjugate pair. This phosphate buffer system is found in the kidneys and helps to regulate blood pH.
We talked about the buffer system in the blood. This is actually a buffer system that's used in the kidneys. It's a dihydrogen phosphate, hydrogen phosphate buffer system. But anyway, the important part here, we added the same amount of HCl to the buffer as we added to the pure water earlier. And the pure water just dropped really fast down to a super low pH because it's a strong acid. If you add the same amount of acid to this buffer system, it went from 6.92 to 6.72. That's just a drop of 0.2 pH units, and that's a lot smaller of a drop than the 4 or so pH units, 5 or whatever it dropped from before. This is the effect of buffers. They resist changes to pH. And again, in our blood and in our kidneys and stuff like that, these are really important because once in a while, if a strong acid or a strong base comes through, you don't want the whole system to shut down. Buffers help protect us, which is a pretty cool thing. Let's consider the acetic acid acetate buffer system to see how they work, all right? So we're going to think about acetic acid and acetate. They're conjugates of each other. Now, the weak acid in the buffer will consume the strong base. So anytime you have a strong base come in, the weak acid, which in this case is acetic acid, will attack it, and they'll wipe each other out a little bit. Well, how much? Okay, let's think about the acetate Kb expression. Now, anytime you have Kb, you have a weak base, in this case acetate. It'll react with water, and the products will be the conjugate acid and hydroxide. This is a Kb because hydroxide is being created, stuff like that. So this is what we talked about in the last section. But what we want to know here is what happens when acetic acid and a strong base hydroxide comes together. And if you remember something we did in the last chapter, we can reverse this reaction. We can write it as acetic acid plus hydroxide, making acetate and water. And when you reverse a reaction, you flip the sign of K, you take the inverse of it. So 1 over the Kb, 1.8 times 10 to the minus 9. Now, why this is kind of cool is because if you have a buffer system where you have both acetate and acetic acid present, if acetic acid sees a strong base, which is what hydroxide is, they'll react very readily to form base, acetate, and water. And they'll form to a K value 1.8 times 10 to the ninth. That's much larger than 1. That's very, very product favored. So if the weak acid and the strong base come in contact with each other, they absolutely attack each other. I would say this reaction goes to completion. You can even write it, if you want, as a single arrow here. That K is so large. So the hydroxide is attacked by the weak acid, and they are wiped out. Now, the weak base does become a bigger concentration when the weak acid and strong base come together. So you saw, like in that last example, when you added the when you added the hydrochloric acid to the buffer system, the buffer's pH did go down. It definitely had an effect, but it wasn't the effect of the strong acid in that case. It was effect of the weak acid being created. In this example, where a strong base is being added to acetic acid, acetate, the pH will also get bigger, all right? But it's not going to be because of the strong base. The strong base is being wiped out by the weak acid, which is there. You just end up with more weak conjugate base. And because it's a base, you will have more of a basic pH. So the pH does go up, but it's from the weak base. It's not from the strong base. So in a buffer, strong bases are attacked by the weak acids, and you will see a pH that goes up, like you'd expect for adding a base, but it's nowhere near as large as if it was the strong base by itself. The pH change comes from the fact that more conjugate base is being created. It is a base, it becomes more basic, but nowhere near as strong as if it would have been like, say, the pure base in water. We can do the same kind of analysis in the opposite process, like what happens when a strong acid attacks a buffer. So we're still going to look at the acetic acid acetate system, but this time we're going to add a strong acid. And to justify what happens here, big surprise, we're going to look at the reaction, the Ka reaction for acetic acid. And all Kas have a weak acid plus water as reactant. They'll have acetate and hydronium as products. And the Ka, if you look it up in the table, was 1.8 times 10 to the negative 5. In this reaction, where we're adding a strong acid to the buffer, and we want to justify what happens, a strong acid is basically a source of hydronium, and a strong acid will be attacked, if you will, by the conjugate base. So, like before, if you flip this reaction around, now you've got hydronium, the strong acid. It's being attacked, if you will, by the conjugate weak base. You're going to make the weak acid and some water. And to justify the K, you can take 1 over 1.8 times 10 to the minus 5. Lo and behold, another very large K. So large that if you wanted to, you could think about it as a one-sided arrow right there. So what this does is it justifies that in a buffer system, strong acids will be attacked by the weak bases. A very product-favored K will result larger than 1. You will end up with more weak acid, all right, than you had before. So the system will be a little bit more acidic, but nowhere near as strong of a pH as if you added the strong acid directly to water. So these last two slides maybe are a little bit weird, all right, but they justify in the scientist's mind why strong acids and strong bases are attacked in a buffer by their opposites. So strong acids by weak bases here. In the last example, it was a strong base plus the weak acid. You end up with a very large K, very product favored. And so we assume that those reactions go to completion, i.e. there's no more strong acid or strong base left. So when everything is done, you do end up with, like in this example, example, more weak acid and less of the weak conjugate base, so it does become more acidic. In the last example, we saw it was more of the weak base relative to the weak acid, so it became more basic. All of these things just justify kind of why buffers happen, all right? And there's a strong propensity for all these strong acids and strong bases to push reactions to the product side. So, Prophet back on again, I guess. If you add a strong acid to a buffer, the pH will go down, but A, it's nowhere near as powerful of a downward trend as if you added the strong acid to water, and B, it becomes more acidic, not because of the strong acid, but because you end up with more of the weak acid at the end, and more weak acid will make the pH go down. So buffers are really fascinating how they work, and it's this weird conjugate system that they can coexist in the same solution, and then as something's attacked by an acid, the base goes to town and takes care of it. On the other hand, if it's attacked by a strong base, then the weak acid kicks in. It's really, really wild, and again, this is what happens in our bodies all the time. This is a graphic representation for kind of what's happening. So in the middle part right here, we've got the original buffer system, and you can see there's a red acid on top and a blue base on the bottom, and roughly the red and the blue parts are the same volume, if you will. Well, if you add a strong base, which is what the hydroxide is, the strong base attacks the acid. So you can see that the acid amount it went up a little bit, but in the process of using up the weak acid, you make more conjugate base, all right? So the strong base does make the pH become more basic, i.e. it gets bigger, but it's not the result of the strong base, it's because you end up with more conjugate base. And the effect of a weak base is certainly smaller on pH than it would be a strong base. Now on the other side, this is the example of what happens when you add a strong acid. And you can see if you look at the middle and the right pictures, the amount of base now has gone down, all right? You end up with more weak acid. Strong acids and weak bases react, and they go to completion. And in the process, you end up with less base. The blue part is less. In the process, though, you also end up with more weak acid. So, to summarize that part, adding a strong acid, your pH does go down, but it's not because of the strong acid, it's because you end up with more weak acid. And that's kind of a neat thing about buffers. Here's a question. What is the pH of a buffer system that has acetic acid concentration equal to 0.700 moles per liter and an acetate concentration equal to 0.600 moles per liter? And we'll use the acetic acid Ka expression. Acetic acid is HOAC plus water. That makes acetate and hydronium. It's a Ka, so it has to make hydronium. If you look up the Ka for acetic acid, 1.8 times 10 to the minus 5. Like before, set up an ICE table, all right? Initially, the acetic acid is 0.700, the acetate 0.600. We don't have any hydronium, so hydronium starts at 0. And like I said, in an equilibrium, you must have some of all species. So hydronium will go up by X, as well as acetate, and acetic acid will go down by minus X. So at equilibrium, 0.700 minus X, acetate 0.600 plus X, hydronium equal to X. You can probably imagine that I'm going to do the 100 times K less than C comparison, because that's how I roll, I know. 100 times K, Ka, would be 1.8 times 10 to the minus 3. That number is certainly smaller than 0.700 and 0.600. Even though initially we could have 0.600 plus X and 0.700 minus X, I'm going to just automatically kick both of those X's out, all right? So we end up with 1.8 times 10 to the minus 5 Ka equals hydronium, which is like X, times 0.600 divided by 0.700, all right? And we'll solve here in a little bit for the hydronium. Hydronium then, 1.8 times 10 to the minus 5 times 0.7 divided by 0.600. That comes out to be 2.1 times 10 to the minus 5 moles per liter. And hydronium, you can turn into pH. pH is minus log of hydronium, minus log 2.1 times 10 to the minus 5. 4.68. Okay, so again, this is a acidic buffer. It's a pH less than 7. That's cool. We have more acetic acid than we have acetate, so it makes sense it would be a little bit acidic. Cool. However, notice that the expression we used earlier was hydronium equals the concentration of the acid divided by the concentration of the base times Ka. Ka, we saw, equaled hydronium times the base divided by the acid, so I'm rewriting it here in this kind of special way. And because the little x was small, you can literally think about just the original concentrations of the acid and the base. You don't have to worry about the little minus x or plus x. Well, people looked at this expression and they rewrote it a little bit as hydronium equals acid over base times Ka, and that's totally fine. You can also have a similar expression with a Kb, and in that version you'd have hydroxide equals the base concentration divided by conjugate acid times Kb. So either one of these expressions work really well, but if you want to find quickly the pH or pOH, if you will, of these solutions, this is a nice way to do it. And again, 100 times K must be less than the C's. If you don't have that, then you should go through the quadratic formula, get out the solve button, all that kind of stuff. If you look at these expressions carefully, hydronium on the left or hydroxide on the right, there's kind of like two components that affects how much acid or base is present, all right? If you look at hydronium, it's the ratio of the acid to the base, all right? And ratios are kind of fun, we're going to see here in a little bit. That's one thing that affects the amount of acid. More acid relative to base, more hydronium, all right? Less acid, then you'd have less hydronium. But the other part is the Ka. And we talked about how as Ka goes up, the strength of the acid goes up. That's what this is saying too. The Ka gets bigger, you end up with more hydronium. For hydroxide, it's a similar kind of thing. Hydroxide depends on the ratio of base to acid as well as the Kb. So there's two factors that affect the pH, if you will, of a buffer. In terms of hydronium, it would be the acid to base ratio. That's one thing. And the Ka would be the other, and you can do it from the other ones if you prefer.